we would like to compute the flux of this vector F across the surface S, where this surface S is this surface, which is part of this plane in the first octant. So what is it? Just like, the plane through 1, 0, 0, 0, 1, 0, and 0, 0, 1, and it's oriented downwards. Okay, so in this case, we are going to compute, as in the previous example, just this vector, and we will have to take negative sign here because it's oriented downwards, and this, this formulation was for n hat pointing in that direction, or we can take cross product in the opposite manner, but whichever way you are comfortable. Okay. Now in this case, it's easy to parameterize this surface because this is x plus y plus z equals 1. So z is 1 minus x minus y. So we can just choose x and y to be the parameters. So now r, the position vector, may be taken as xy, and then for z we write 1 minus x minus y. So r is a function of two parameters, and it traces this surface, and we are looking at it at this surface restricted in the first octant. So now, as an example 1, with this formulation of r, this changes to, I forgot the negative sign here, I'm so sorry. Okay, let me just put it in. Okay, so this integral changes to this with this formulation of r, as we did in the example 1, and a is going to be, let me make it bolder. So a is going to be this region, the parameter domain for x and y. So let's go ahead and compute this integral. Okay, so we have to compute this integral where f is given by this quantity and r is this. So dr dx will be 1, and that of y, the derivative, would be 0 with respect to x. And here I got only this part as a function of x, so that gets to be negative 1. Then we have dr over dr dy, 0. And then derivative of y is 1. And here that of this whole quantity, only negative y is differentiated with respect to y. So we get negative 1 here. So now what we will do is we will compute the cross product. So let's do so. So cross product of these two vectors would be, simply we just go to our routine method of writing the cross product as a determinant. And what we get here is I, j, k, again 1, 0, negative 1, then 0, 1, negative 1. So what we get here is this, that first, for the first component, we have 0 times negative 1 is 0. Then we will have minus negative 1 times 1 would be 1. And then when we go for the cofactor of j, here we have 0. Then again we have negative of negative 1. That will be positive 1. And then when we go for cofactor of k, we look at this, and here 1 times 1 is simply a 1. So what we get now is, for this quantity, is that it's easier than our first example, isn't it? So here we go, and then we have dot product with 1, 1, 1. So all that will happen is this, that all these quantities will just add up with each other, right? So what do we get here is this. So this would stay as minus, and here this will be added here. Okay, so what I did was this times xz to the y times 1 is that, and then negative xz to the y times 1 is right here, and these two quantities will do what? they will simply cancel each other. So when that happens, we simply get, so what do we get here? This whole thing just comes down to being z. Okay, so what we have to do now is we just have to compute this integral. So now it has become much easier actually, right? Because this whole thing has become the integral over the region D, which we are going to go over, okay, of simply that of z. Okay, so let's proceed with this. So okay, so let's come back to this picture. First of all, I made like a bad statement here. This region is actually D, the region over which we are integrating, where the parameters x and y are taking values. So this region, if you note, that is simply the region where, or in a way, this is the x-axis, okay, and this is the y-axis. So what will happen is we'll take a thin element here, okay, and what does z become here? Remember this portion, or let me just erase this and bring in our calculation in here. So first we are going to clear the board here, okay, and yes, I think this will suffice for now. Okay, so what we had was this, that our integral just came down to being this, right? And we know that our z is how much? 1 minus x minus y, right? Okay, so we will write that down. So we have 1 minus x minus y, and then let's say, and that's what z is, and this you can see this intercept is 1, this is 1. I'm not writing the other coordinates here, treating them as understood. So say we let y vary first here. Okay, so what will happen is, you can see this equation here is what? Y equals 1 minus x, right? So we will integrate with respect to y and go from 0 to y equals 1 minus x, and then of course now x is going to go from 0 to 1. Okay, so if we go ahead and find this iterated integral, which we are going to. So now we are back here. So let me just write down the values that we determined in the last part. That is, the limit of x are from 0 to 1. Those of y are from 0 to 1 minus x. Then we are integrating 1 minus x minus y. All right. First with respect to y, then with respect to x. So what we get is here the outer portion, okay, and then you have we are integrating with respect to y, so we'll get y minus xy then, and then minus y square over 2, or 1/2 y square, right? And and here the upper limit is 1 minus x. The lower limit is how much? That's 0. And then we got dx. So this becomes equal to, okay, what will this be? This would be, we got 1 minus x here. So let me just write it down. This is 1 minus x. And then y becomes 1 minus x again. All right. And then we get 1 minus x square. All right. And since we have y present explicitly in each step at 0, this will all be 0, right? Okay. So this whole thing simply becomes the evaluation of this integral, which is an easy polynomial for you to integrate. So I'm just going to leave the details on you. So the value would be how much? The flux would be -1/6. Okay.